Hello, hello, hello. Here we are with our rational zero theorem. This is section 5.5. So basically what we want to do in this lesson is find all of the zeros of a polynomial. Remember, a zero is the x-intercept. It's a root. It's the factor of that polynomial. Well, that's really easy when the polynomial is factorable. But what happens if it's not factorable? That doesn't mean that it doesn't have real zeros, that it doesn't cross the x-axis. So this rational zero theorem is going to give us a way of finding those zeros. So we're going to kind of start off with a review, and it says prove that 1 is a 0 and then factor completely. So I'm kind of telling you, hey, 1 is a 0, prove that to me. So what you could do for this instance is you could use your synthetic division. 1 being here, because if a 0 is 1, then the factor would be x minus 1, right? So we could divide using synthetic division. And I could do my 1, 0 for the x squared term, negative 7, and then 6. Drop down the first term. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1. Negative 7 plus 1 is negative 6. Negative 6 times 1 is negative 6. And here we go. We get that remainder of 0, which means that 1 is a 0. So we just proved that 1 is a 0. So that means if I were to factor x cubed minus 7x plus 6, I know that x minus 1 is a factor, and then that factor times the quotient. And our quotient here is x squared plus x minus 6. Remember, we always start our quotient with 1 degree less than the dividend. And if our dividend had a degree of 3, then our quotient down here has a degree of 2. And you remember, if this is the remainder, then this is the constant, this is the x term, this is the x squared term. So that's another way that you can kind of remember that. And so here we have x minus 1 times x squared plus x minus 6. Well, I'm not done factoring. It says factor completely. So I want to look at that trinomial and I want to ask myself, can I factor it? Remember, when factoring, you always want to look out for a GCF first. There is none here. We know it's a trinomial, so we have kind of 3 different options. We're either saying that A is 1, we can use the AC method. A is not 1, we can use the AC method and factor by grouping. Or it could be a perfect square trinomial. Well, I hope that you can tell that this is not a perfect square trinomial, and our A value is 1, so we're going to use the AC method. So 1 times negative 6 is negative 6. Factors of negative 6 that add up to a positive 1. That's that B term, and that's going to be a negative 2 and a positive 3. So now it is factored completely. So I just kind of, like I said, we just want to throw that in at the very beginning for a review so you understand what that division is doing for us. If we know a factor, if we know a 0, we can divide, and then remember that quotient is what's being multiplied to that divisor. So like I said, what if it's not factorable? You know, what if I give you some polynomial and you can't factor it, but you graph it and you have these real zeros, it's crossing the x-axis. So the rational zero theorem is going to help us get those zeros. So this is kind of hard to understand, so bear with me. If p of x is a polynomial with an integer or with integer coefficients, okay, so that's first part should make total sense to you, okay, that's what we've been dealing with. Polynomial with integer coefficients. Notice we haven't been doing anything with fractions or decimals for coefficients. Okay, then it says, if m over n is a 0 of the polynomial, then p of that number, m over n, is equal to 0. Remember, that means if that's a 0, I'm getting a remainder of 0. So when I plug it in and evaluate, I will get that remainder. Remember, that's a property of synthetic division. And then what are this m and n representing? Well, this is where it says, then m is a factor of the constant term, and n is a factor of the leading coefficient. Again, these are terms that you should already know. So this m over n, that's a number. And how they're getting that number is taking the factors of the constant term and putting it over the factors of that leading coefficient. Okay, that's exactly what this is saying here. Now, we actually don't use the letters M and N because they're kind of hard to differentiate. That's why I'm enunciating very clearly. So we actually use P and Q because that's way easier to kind of differentiate. So to find those possible rational zeros of a polynomial, we take P over Q. Those are going to be the factors of the constant term. So same thing here, factors of the constant term. And then Q is going to be the factors of those leading coefficients. Again, same thing there, factors of the leading coefficients. So we're taking the same thing, we're just changing up the letters just to help us out. So one really, really, really important word in this box is possible. Notice it's italicized and underlined. To find the possible rational zeros of a polynomial, we're going to take the factors of the constant term and put it over the factors of the leading coefficient. So that means we could end up with some fractions, but that's okay. Possible means it could work, but it could not work. So yes, if your brain is kind of screwed on and you have your thinking cap on, what we're saying here is we're going to make a list of possible zeros for the polynomial, but that means not all of them are going to work. So then we're going to have to go through this like kind of picking and choosing and guessing and checking of which ones work and which ones don't work. I know that kind of sounds like it could be frustrating and hard, and it might be for some questions, but not all of them. I promise you that. All right, so let's go ahead and get started. So example 2, part A and B, really simple. We just want to start off with listing the possible rational zeros. So remember, this is for problems whenever I give you a polynomial and you can't factor it. So yeah, even though A has a GCF of 2, if you take that out, you wouldn't be able to factor it. So we would have to do this rational zero theorem. And the first step in doing the rational zero theorem is coming up with the possible zeros. So taking P over Q. So here we go. P. I'm going to make a little list. So P are going to be the factors of -8. So what are the factors of -8? Well, we have +1 and -8 or -1 and +8. So that means I have a plus or minus 1 and 8. Other factors of -8 are a +2 and a -4 or a -2 and a +4. So that means I also have a plus or minus 2 and a plus or minus 4. You don't have to list these out in order. It's just I know the method here, so I know that I personally want to put them in order from least to greatest. Whenever we're listing out these factors, we're always going to include the positive and the negative of that number, because think about it. If I have a positive number and I'm trying to find the factors of it, I can multiply a positive with a positive or a negative with a negative. If I'm trying to find the factors of a negative number, I know I have to have a positive and a negative. So therefore, no matter what kind of number you're finding the factors of, you have to include the positive and the negative of those factors. Okay, so that's it for the factors of the constant term, which is -8. That's our quote-unquote P value. We also want the Q value. And Q value is the factors of your leading coefficient. Well, here's my leading coefficient, a +4. Well, that means I want a plus or minus 1, 2, or 4. So in total, I have 8 P values and I have 6 Q values. What we want is P over Q. All right, we want P over Q. This is our goal here. So here I go making another list. So what I like to do here is I like to take all of my P's and write them over Q and just kind of go down the list. So I could still have a plus or minus 1 over 1, which is 1, 2 over 1, which is 2, 4 over 1, which is 4, and 8 over 1, which is 8. Moving to the next Q value, I could have a positive or negative 1 over 2, 2 over 2, which is 1, and it's already in my list, 4 over 2, which is 2, which is already in my list, and 8 over 2, which is 4, which is already in my list. So that was nice. And then moving to that last Q, I could have a 1 over 4, which is 1/4, 2 over 4, which is 1/2, which I already have written down, or 4 over 4, which is 1, which is already in my list. So notice we don't have to write, or we most of the times don't have to write every single scenario, because a lot of them are going to repeat themselves. So that's really nice. So yes, these are the possible zeros of the polynomial 4x cubed plus 2x squared minus 8. Our list here includes 12 possibilities: +1, -1, +2, -2, +4, -4, +8, -8, +1/2, -1/2, +1/4, -1/4. You got the idea. what you're going to learn a little bit later on is that degree of the polynomial is going to tell us something very important, okay? And you might already have an idea of it, but for right now, this is all we want to practice is just finding those possible rational zeros, and this is it right here. This is our answer, okay? All right, let's go to the next one. So we have 6x to the fourth minus 3x cubed minus 2x squared, excuse me, plus 5. All right, P over Q. Here we go. Excuse me, P. Those are the factors of the constant term, plus or minus 1 and 5. We love prime numbers when we're listing those P's and Q's. Prime numbers means it's only divisible by 1 in itself, so that's going to be really helpful. All right, and then our value of Q here, plus or minus, remember that's the factors of that leading coefficient, so that would be 1, 2, 3, and 6. So now I want to list out my P over Q values. So P over Q, again, you know it's always going to be positive and negative. 1 over 1, 1 over 2, 1 over 3, 1 over 6, and then 5 over 1, 5 over 2, 5 over 3, and 5 over 6. So this one gives us a little bit more kind of like nastier P over Q values, just because, I don't know, we just had a lot of those fractions, so it kind of feels like it's going to be pretty gross. But we don't have to do anything with this one, so that's nice. We're just listing out those possible rational zeros. Okay, so maybe you're thinking to yourself, what are we going to be doing? Well, again, I want to stress the importance of knowing how to factor and understanding what is factorable and what is not factorable. So what we're going to do in example 3 is we're going to factor and find all the zeros. So in this 2x cubed plus x squared minus 13x plus 6, my first thing I want to know is it factorable? Is there a GCF? No. It has 4 terms, so I would factor by grouping. Just looking at it really, really quick, I know the GCF in the first 2 terms would be x squared, leaving me with 2x plus 1. And the GCF in the last terms is just a negative 1, and I'm not going to get that 2x plus 1 inside the parentheses. Because those 2 parentheses are not the same, that means it's not factorable. So this means I need to list out my P over Q value. So here's where I'm going to kind of show you what do we do with those possible rational zeros. So let's make our chart really quickly. So I want to know what my P over Q values are. Well, this is my P. Well, here, let me break it down again. P is going to be plus or minus 1, 2, 3, 6. Q is going to be plus or minus 1 or 2. So that means P over Q is going to be plus or minus 1, 2, 3, 6, 1/2, 3 over 2, 6 over 2, but that's really just 3. So here's my list. I have 1, 2, 3, 4, 5, 6, 12 possibilities. So what do I do with those 12 possibilities? I pick one. I pick one and I plug it into synthetic division setup to see if it works. What do I mean by if it works? I mean, if I plug in, let's say I pick 2. Okay, let's say I pick positive 2. So let me change colors real quick. Let's say I pick positive 2 and I want to set up my synthetic division. Well, that would be 2, that would be 1, that would be negative 13, that would be 6. I want to see if it works. And what I mean by if it works is if I get a remainder of 0 here, that tells me that x minus 2 is a factor of this polynomial, which means then I can divide it out like I'm doing with synthetic division, get that quotient, that's going to be what it multiplies with, okay? If I don't get a remainder of 0, let's just say I get 4 here, well then that means x minus 2 is not a factor of it, so I'd need to pick another number from my list. So yes, this can get very quote unquote guess and checky. That's kind of the whole idea behind it, but there's no other better way to do it. Okay, all we know is what the possible zeros are, and then it's up to us to kind of figure out which one is and which one's not. So, like I said, let's just try 2. So drop down that 2. 2 times 2 is 4. That would be 5, 10, -3. Oh my God. Oh my God, that was awesome. It worked. I got a remainder of 0, which tells me that 2x cubed plus x squared minus 13x plus 6 actually factors into x minus 2 times 2x squared plus 5x minus 3. This is wonderful. This is wonderful. Okay, so now I can't do anything with the x minus 2. That's all, okay? But that 2x squared plus 5x minus 3, I want to ask myself now, can I factor it? If I can, I factor like normal and go about my day. If I can't, I do this p over q thing all over again, and I'm going to get a new list of possible rational zeros just for that trinomial, okay? But let's look at it. 2x squared plus 5x minus 3. Factor. Is there a GCF? No. It has 3 terms. Is it a perfect square trinomial? No. AC method. So -3 times 2 is a -6. Are there factors of -6 that add up to a +5? Ding, ding, ding. Yes, there are. It's +6 and -1. All I need to do is factor this by grouping now. So let me make this a teeny bit smaller. Let me make this a little bit smaller, move it up. Okay. So, let me just kind of do that. Okay. So, x minus 2, 2x squared plus 6x minus 1x minus 3 means I'm going to have 2x leaving me with x plus 3, -1 leaving me with x plus 3. Hallelujah, praise the Lord. So that means my factors are x minus 2, 2x minus 1, and x plus 3. Boom, shakalaka. Now look how cool this is. The 0 here is 2. We knew that. The 0 here is a +1/2. It's right there. 0 here is a -3. It's right there. Isn't that awesome? So I randomly picked the +2 first, and it worked. If I would have picked the +1 or -1, it wouldn't have worked. If I would have picked the -2, it wouldn't have worked. But my next guess probably would have been a positive or -3. It would have worked. Probably wouldn't have tried the 1/2 or the 3/2, but that's okay. It worked. It wouldn't have been that hard, okay? But isn't that so cool? I just think this is awesome. But like I said, it's really, really important that you know from the very beginning, is it factorable or not? Because if it's not, or if it is, and you go through this list and kind of waste your time guessing and checking, you're going to be really mad at yourself if you look back and say, oh my God, that was factorable. Like, ugh. So anyways, okay, let's try another one. So let's look here. X to the 4th minus 6x squared minus 27. So first thing is it factorable? So GCF, no. There's 3 terms. It's not a perfect square trinomial. So we're going to go with the AC method. So A is 1 times that C of -27. That's -27. Are there factors of -27 that add up to a -6? Yeah, there are actually. And that's going to be -9 and +3, right? -9 and +3. Not -9 times 3 is a -27. -9 plus 3 is -6. Hallelujah, praise the Lord. Okay, so that means because this is 1, I can rewrite this as x squared minus 9 and x squared plus 3. So I factored. Okay, I need to look at those individual factors and see if they can factor some more. X squared minus 9, is it factorable? Let's go through the list. Is there a GCF? No, it has 2 terms. Is it the difference of squares? Yes, it is. X squared is a perfect square. 9 is a perfect square. They're being subtracted. So I know that that is going to factor into x plus 3, x minus 3. Let me look at that second one, x squared, good sign. Oh, plus, boo, 3, not the sum or the difference of cubes because neither one of them are a perfect cube. So that's actually not factorable. So we leave it as x squared plus 3 and boom, this is factored completely. So let's take it a step further because the directions say factor completely. That's what we did. And find the zeros. Well, I know you know that this is a 0 of -3 and this is a 0 of 3. But this last one, remember we're setting this equal to 0 and solving. And what happens when you take the square root of a negative number? Plus or minus I root 3. Okay. Anytime you take the square root of a number, you got to include the positive and the negative of it because it was a negative underneath the radical. Remember, we pull that out and it becomes an I, that imaginary number. Okay. So that means, I'll just write it over here, that x can also be plus or minus I root 3. So these are my zeros. Now let me show you something. How many zeros are here? Real and imaginary. We have 2 real, 2 imaginary. That's a total of 4. Over here, how many zeros did we have? 3 reals. I think it's a coincidence. I don't know. Okay, let's try it again. This one just says factor. Okay, just says factor. So this bad boy has 5 terms. On our factoring notes from last class period, we didn't have something that said 5 terms. So we have to use the P over Q method. Okay, and there's no GCF, so it's not like that'll help us anyway. So we're just gonna get started. Okay, so P. Plus or minus 1, 2, 3. Yes, 4, 6, 8, 12, 24. Is that right? 1 and 24, 2 and 12, 3 and 8, 4 and 6. Yeah, okay. So that's P. Ooh, Lordy. Q, just plus or minus 1. Thank God. Well, then that makes our P over Q very easy because all of those P's over Q are just those numbers. So I'm actually just going to erase this and put that this is P over Q. Okay, that's pretty cool. All right, so here's our list. And like I said, here's the kind of tough part. This is probably the hardest part of the whole thing, is just picking a number and hoping it works, right? And don't feel defeated if you pick a number and it doesn't work. You just have to try again. It's not a big deal, okay? And just because, let's say we pick a positive 1 and it doesn't work, that doesn't mean that the negative 1 won't work. So keep in mind you have the positives and the negatives of these numbers. So really you have 16 numbers to pick from. 1, -1, 2, -2, so on and so forth. So let me change colors. So, all right, so pick a number. I think you said, let's go -2, just to be different. All right. So then I list my coefficients. 1, -4, -7, 22, 24. And then this is, again, where your skills really come into play. How fast are you with the synthetic division while still being accurate? 1, -2, -6, 12, 5, -10, 12, not, oh, wait, oh, yes, y'all, that was so random. How did I get so lucky? That's awesome. Okay, so it works. So I'm gonna make that a little bit smaller. So let's write what this gives us. This means that -2, -2 is a 0, which means x plus 2 is a factor. What did x plus 2 get multiplied with to get our original polynomial? The quotient here. So that's going to be x cubed minus 6x squared plus 5x plus 12. Okay, now we look at what's left in the parentheses and we ask ourselves, is it factorable? So I'm looking through real quick. It has 4 terms. If I factor by grouping, it's not going to work. So I have to do my P over Q list again with this as the polynomial. I don't care about this. That's already been factored. I'm keeping that from here on out. What's changed is this polynomial right here. Okay, so listing those P over Q values, again, my Q value is 1, which means all of the factors of P are going to be the P over Q values, which is great news, right? So P over Q is going to be plus or minus factors of 12. So 1, 2, 3, 4, 6, 12. Okay, so I'm going to pick another number from this list. This time my favorite number is 4, so I'm going to go with 4. So I'm going to pick 4 up here. I'll write down the coefficients of this polynomial now. 1, -6, 5, and 12. Oh, -3. Oh my God. That's awesome. I swear, I'm just like picking numbers. I promise you. Okay, so now let's write what this means. We have x minus 4 is a factor, leaving us with x squared minus 2x minus 3. But don't forget about this guy right here, okay? So we still have him as a factor. So that means I'm going to go ahead and just put him right here. Okay, I probably should have changed colors. Let me do that. Let's see if that worked. Sweet. Okay. Okay, so here's what we have. Now, don't need to worry about him. Don't need to worry about him. Yes, I need to worry about this one. Okay. First things first, is it factorable? 3 terms this time. Is there GCF? No. Because it's 3 terms, A value is 1. Let's look at the AC method. 1 times -3 is -3. Factors of -3 that add up to -2. Hallelujah. Praise the Lord. That's -3 and +1. I can factor this, and that is going to become x plus 2, x minus 4, x minus 3, and x plus 1. Yay! And look, a 0 of -2, a 0 of 4, a 0 of 3, a 0 of -1, all in the list. So if you would have started off by picking the -1, you would have gone through a process and it would have worked. If you would have started off by picking the +3, you would have gotten a remainder of 0, been left with a quotient, you would have done it with the quotient, so on and so forth. So here's another place where answers are going to look completely different depending on how you start and, you know, if you recognize factoring or not. So there are multiple ways that this problem could have been done. So just keep that in mind. But here again, let's just look at it really quick. How many zeros do we have? We have 4 real zeros. What is the degree of the polynomial? 4. Okay. Earlier I said, do you think that's a coincidence? Well, it's actually not, and here's why. The fundamental theorem of algebra. Every polynomial function of a degree of n greater than or equal to 1, so a degree of anything 1 or bigger, has at least 1 0, where a 0 may be a complex number. But then there's a corollary to that, kind of like an addendum, if you will, and it says every polynomial function of degree n greater than or equal to 1 has exactly n zeros, including multiplicities. So let's think about what that means. If we factor something and we get like x plus 1 squared times x minus 3, well, this is technically 3 zeros, right? This is 2 -1s and then a +3. So that is actually 3 zeros. So that's what it's talking about, including the multiplicities. But yeah, isn't that really cool? So that also ties in, like we kind of touched base on it when graphing our polynomials. Whenever we were factoring them based on the degree, most of the times we had that many x-intercepts. Not always, because we were only getting real x-intercepts. And you're going to see later on that we can have complex numbers. So, you know, remember that are the imaginary numbers. Like kind of like what we saw right here in B. Those are 4 zeros. 2 of them are real and 2 of them are imaginary. So if we were graphing that, we wouldn't see the imaginary numbers on a calculator or even if we were sketching a graph, but they're still there. And that's why the polynomial has a degree of 4, is because there was 2 imaginary and 2 real. All right, so we just have these 4 questions left. All right, so what we want to do is find all the zeros. So it's kind of what we've been doing. Remember, we always want to check to see if it's factorable first. So that way we don't do this whole guessing checking method of p over q. So I see x cubed minus 64. Well, if I want to go factor, I look out for a GCF. There is not one. I ask myself how many terms there are. There's 2 terms, and I see that this is the difference of cubes. So remember, how do we factor the difference of cubes? The first thing, because x cubed is a cube and 64 is also a cubed. That is 4 cubed. 4 times 4 is 16 times 4 is 64. So the first thing we do is we create our binomial by taking the cubed root of the first term, keeping the sign, and taking the cubed root of the second term. The second thing we do is we scums the binomial. Remember, that's SCMS. Square the first term, change the sign, multiply the 2 together, and square the last. Now, this is factored completely, but that's not what the directions ask for. The directions say find all the zeros. And so I know that in this first factor, I have a 0 of 4. But this second factor, the trinomial, is not factorable. Can you go through your p over q method? Absolutely. And you would have plus or minus 1, 2, 4, and 8. But you also need not forget how to solve a quadratic that's not factorable. Dun 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 dun. 1, 2, 3. X is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. So I can solve it using quadratic formula as well. It might be quicker. It might be not as quick as p over q method. It's just kind of up to you. Again, I just kind of wanted to put it back in your brain. So solving this out, we would get negative 4 plus or minus the square root of, let's do some quick math. 4 times 1 is 4. 4 times 16 is 64. 16 minus 64. 16 minus 64 is a negative 48. So we have a negative 48 underneath the radical, and that's being divided by 2. We know that this is going to be an imaginary number. It's going to be a complex number. So I need to figure out, this is going to be I and 48. So factors of 48, well, we could go 4 and 12. This is 2 and 2. Let's go 2 and 6. And then let's go 2 and 3. So that's going to be boom, boom. That's 2 times radical 3, which is 4 radical 3. So this is 4i radical 3. The square root of negative 48 is negative 4 plus or minus 4i radical 3 over 2, which will then reduce to negative 2 plus or minus 2i radical 3. And those are my 2 zeros. So let me erase that. And then let me shrink this down. And then let me actually just take this and go here. Okay, so we have 4, that's 1, and then we have negative 2 plus 2i radical 3, and negative 2 minus 2i radical 3. So in total, that's 3 zeros, degree of 3. Oops. So that's right that we should have 3 zeros. 2 of them are imaginary, 1 of them is real, and that's okay. We don't know how many are going to be real, how many are going to be imaginary, but we do know the total amount, and that's always the degree of the polynomial. All right, so then let's look at part B. We have x to the 4th minus 16. So first thing is there a GCF? No. Second thing is there are 2 terms, and we see that this is the difference of squares. X to the 4th is a perfect square. So remember the square root, let's go green. Let's go, yeah, that's fine. All right, so the square root of x to the 4th is x squared. The square root of 16 is 4. Difference of perfect squares have a positive and a negative. And so then remember, you always want to check those factors to make sure that they won't factor any further. X squared plus 4, Well, it's very close, but it's not a difference of squares. However, x squared minus 4 is a difference of squares. So now it factors into x squared plus 4, x minus 2, and x plus 2. And so that's factored completely, but I want to find all the zeros. So this is going to give me a 0 of 2, negative 2, and then this is going to be 2i, plus or minus 2i. So, oh, sorry, my doggy. So in total, how many zeros are there? Well, 1, 2, 3, 4. 4. 2 real, 2 imaginary. All right. Oh. And here we go. Almost done. All right, so solve the polynomial by finding all of the zeros. So kind of the same thing. So remember, this time we want to always make sure that if it's factorable, factor it. If it's not, we're going to have to use the P over Q method. Again, right here, kind of going through my steps of factoring, there's no GCF. It has 4 terms, so we would factor by grouping. Looking at factoring by grouping, I know that it's not going to work out. I can just look at it and see because my brain's doing it so quickly. So I have to do the P over Q method. Again, luckily for us, it's just going to be factors of P that are the P over Q because Q is just 1. So we have plus or minus 1, 2, 3, 4, 6, and 12. So yeah, there are 12 possible numbers, but we'll see. So I'm going to go with 2 first, a positive 2. So let's see what happens. 1, negative 5, 2, 12. Nope, didn't work. So see, you're not always perfect the first guess. So it didn't work. Oh well, no big deal. All right, so let's try another one. Let's go 3. Okay, so I'm going to go 3. Boom, boom, boom. Still 1, negative 5, 2, and 12. 1, 3, negative 2, negative 6, negative 4. Oh, yay. Okay, so this one did work, so it had a remainder of 0. So what does this tell us? This tells us that x minus 3 is a factor, and that's being multiplied to x squared minus 2x minus 4. So then I want to look at that trinomial, x squared minus 2x minus 4. No GCF, 3 terms, AC method, factors of negative 4 that add up to negative 2. Negative 4, positive 1, negative 2, positive... it's not factorable. Boo. Well, let's just try to do quadratic formula again. Unless you want to do P over Q, that's fine too, but I'm right here. So technically this is going to be x is equal to negative b plus or minus the square root of b squared minus 4ac all over 2a. All right, and so then that's going to give us 2 plus or minus the square root of 4 plus 16, which is going to be 20 over 2. So then I come over here, do this real quick, 2, 10, 2, 5. So this is going to be 2 radical 5. So 2 plus or minus 2 root 5 over 2, which is just going to reduce to 1 plus or minus the square root of 5. So I'm going to erase all this. And then this gives me x minus 3 and then x whatever. So I'm actually going to erase this. This means that x equals 3 and x equals 1 plus or minus root 5, which is not imaginary, it's just irrational. Okay, it's irrational, not rational. So this is 1, 2, 3 zeros, 3 zeros. Cool. And last one. So again, looking through, I know there is a GCF of x. I could take that out, but oh wait, this one actually might. Oh yeah, this one might work. Okay, let's see. So GCF of x leaving me with x to the fourth minus 2x cubed plus 8x minus 16. And then looking at those four terms, factor by grouping. So first two terms would be x cubed, leaving me with x minus 2. Last two terms is a positive 8, leaving me with x minus 2. Sweet. So this means we have x times x cubed plus 8 times x minus 2 equals 0. And then I want to double check my factors just to make sure. Well, this is going to be 0. This is going to be 2. But that middle factor can actually factor some more because it is the sum of cubes. So to factor that, remember we take the cubed root of the first, keep the sign, the cubed root of the last, and then we scums it. Square the first, change the sign, multiply the two together, and then square the last. So then I want to go through and I say, okay, well, this is giving me an x of negative 2. And then I want to look through here at this trinomial and I want to say, well, can I factor it some more? What are the zeros there? Well, factors of 4 that add up to negative 2, it's not factorable. So quadratic formula or P over Q, I'm going to do quadratic formula. Opposite of B plus or minus the square root of B squared minus 4 times A times C all over 2A. 2 plus or minus, it's going to be a negative 12 over 2. So then that means this is going to be 2 plus or minus 2I root 3 over 2, which is just 1 plus or minus I root 3. So there's 2 zeros, 3, 4, 5, 5. That's exactly how many I wanted. So that one, you didn't have to do, the guessing and checking, but it took a while to factor because you wanted to make sure you had every single zero for that polynomial. Hope you didn't get too lost or confused. It's really not that hard if you know you're factoring. All right, guys. Talk to you later.